Preserving aviation history is usually a question of depth. Out in the open ocean, great depth can act as a shield, sealing wreckage away from oxygen and human interference, while exacting a steep price from any recovery effort. In the shallows, that same factor turns hostile, letting wave energy and surface traffic tear aluminum into unrecognizable fragments. But in the mangrove swamps of northern Australia, depth is not a constant at all. It rises and falls by the hour, and the primary constraint is the precise timing of the lunar cycle. In the east arm of Darwin Harbor, there is a specific coordinate that remains invisible for the majority of the year. The water here is opaque, a suspension of silt and organic matter that drives visibility to near zero. A diver could swim directly over it and never know it was there. Sonar struggles against the soft return of the mudbank. To see the target, one does not use sensors. One uses a tide table. The target is the wreck of a 24-1. This specific airframe holds a unique distinction in the registry of the Royal Australian Air Force. It was the very first consolidated PBY-5 Catalina flying boat delivered to Australia. It arrived at Rose Bay on February 2, 1941, flown by Qantas Captain Lester J. Brain, with the legendary navigator P. G. Taylor on board. It served through the entirety of the Pacific War, a flying long-range patrol and mine-laying missions, while newer aircraft were lost to enemy fire and operational accidents. It operated through the years when Singapore fell, when Darwin came under attack, and when the fight pushed north into the Solomon Islands. Yet it sits here today, broken and embedded in the mud, not because of a combat action, but because of a failure that occurred after the surrender of Japan. The wreckage lies on a tidal mudflat that is exposed only when the water level drops below 2.5 meters. In Darwin, the tidal range can exceed 8 meters, moving billions of tons of water in and out of the harbor twice a day. This massive hydraulic cycle creates a dynamic boundary for any survey operation. At high tide, the aircraft can sit under several meters of turbid water, depending on the cycle. At low tide, the water recedes, but it leaves behind a defensive perimeter of deep, stabilizing mud. Access begins with a tide table, not a tank on your back. It is a walking survey, conducted in an environment that is hostile to human physiology. From a distance, the flats look firm, but the surface behaves like wet cement, dragging at legs and swallowing equipment. The terrain is only the passive hazard. The active hazard is biological. The east arm is crocodile water, apex predators in the murk at the mangrove edge. Any investigation of this site must balance the scientific requirement for documentation against the operational risk of exposure. The survey team cannot simply swim down to the wreck. They must wait for the harbor to drain. When the tide hits that critical mark, the dorsal section of the fuselage begins to break the surface. As the water drops further, the stumps of the parasol wing and the shattered remains of the hull become visible. This reveals the scale of the artifact. The PBY-5 is a massive machine, with a wingspan of 104 feet and a maximum loaded weight on the order of 35,000 pounds. Even in its fragmented state, the footprint of the debris field is significant. The objective of modern archaeological work here is not recovery, but identification and forensic mapping. The team must confirm that this is indeed A24-1, not one of the other flying boats lost in the harbor, and read the rivets and metalwork closely enough to distinguish a pure PBY-5 from the amphibious PBY-5A variants that also operated in this theater. And it all has to happen within the tide's working window. This creates a rigid operational window. A survey team gets only a brief working window on the flats before the tide turns. Once the water begins to rise, it moves quickly, flooding the mudbank and hiding the aluminum beneath the surface once again. There is no margin for error. If a surveyor is stuck in the mud when the tide reverses, the risk profile shifts from equipment loss to fatal encounter. The study of A24-1 is a negotiation with the environment. We do not control the site. We are granted temporary visitation rights by the physics of the solar system, and we must gather our evidence before the water closes the gate. On August 30th, 1945, the Pacific War was over in all but paperwork. Japan's surrender had been announced on August 15th, and the formal signing would follow on September 2nd. A24-1 was tasked with a transport mission to Singapore, carrying medical supplies and personnel to assist prisoners of war. The aircraft was fully fueled and loaded near its maximum authorized weight for a water takeoff. The conditions in Darwin Harbor that morning were deceptively calm. Light winds and a smooth surface made the water look harmless, a mirror that erased depth cues. In maritime aviation, this is glassy water, and for a flying boat, it is a trap. Without small waves to feed air under the hull and break surface tension, the aircraft can struggle to transition from displacement mode to planing mode, getting on the step. The penalty is stiction, the drag increase that forces the engines to fight not only weight and air friction, but the water's own grip on the metal skin. Wing Commander Keith Baulitho, the pilot in command, initiated the takeoff run. As the aircraft accelerated, the hull refused to climb cleanly onto the step. In this regime, the pilot faces a binary choice. He can abort the takeoff, taxi back, and reduce load or wait for better surface conditions. Or he can attempt to force the aircraft into the air by increasing the angle of attack. Baulitho chose to continue the run. He applied back pressure on the controls, trying to lever the nose up and break the suction. This decision triggered a violent instability known as porpoising. It is a runaway oscillation between the hull and the water, where the aircraft alternately climbs onto the step and then falls back off it. The bow rises, the planing angle collapses, and the next contact with the surface hits harder than the last. Each impact feeds the next pitch cycle until the motion stops being a nuisance and becomes a structural event. A24-1 entered a diverging oscillation. The cycles of pitch up and slam down increased in amplitude with every second. The structural limits of the hull were exceeded. On the final impact, the metal skin compromised. The hull split open and water rushed into the bilges. The aircraft lost all forward momentum and began to settle into the harbor. The loss of the airframe was now inevitable, but the loss of the cargo was not. The aircraft did not sink immediately. The watertight compartments provided enough residual buoyancy to keep the wings above the surface. Recognizing that the deep channel would claim the entire machine, a workboat was dispatched to attach a tow line. The objective was not to save the plane for flight, but to ground it before it could submerge completely. This operational decision created the primary archaeological signature of the site today. The wreck of A24-1 does not lie where the accident first unfolded. It lies on the intertidal mudbank of East Arm because it was deliberately towed and beached there to make salvage possible on the falling tide. Once the hull was grounded, the crew was able to offload the 9 passengers and the medical supplies without injury. The tide receded, leaving the broken aircraft high and dry. In the weeks that followed, the Royal Australian Air Force stripped the cockpit of instruments and removed what equipment it could reasonably salvage. The empty shell was then abandoned. The damage to the keel and the bulkheads was too severe to justify a repair, especially with the war over and hundreds of surplus Catalinas available. Towing saved the payload and left the airframe to die slowly by corrosion. The identification of a submerged aircraft is usually a process of matching serial numbers to a loss ledger. However, in the turbid waters of Darwin Harbor, the aluminum skin of a wreck is often too corroded to read painted stencils or stamped data plates. The environment scrubs away the surface details, leaving only the gross structural geometry. To identify the wreck in East Arm, the survey team had to rely on a fundamental design contradiction between 2 variants of the Catalina airframe. There are multiple Catalina wrecks in Darwin, but they fall into 2 distinct mechanical categories. The PBY-5A is an amphibian. It carries heavy retractable landing gear, allowing it to operate from concrete runways as well as water. The PBY-5, the earlier model, is a pure flying boat. It has no wheels, no brakes, and no hydraulic retraction mechanisms. It is a vessel designed exclusively for the water, requiring a beaching crew and detachable beaching gear to be hauled up a ramp. A24-1 was a PBY-5. It was delivered in 1941 before the amphibious variant became standard in the theater. Therefore, one strand of forensic proof lies in what is missing. If the wreck in the mud possessed the large rectangular wheel wells required to house main landing gear tires, it would point toward an amphibious variant. If the hull remained continuous and smooth through that section, it would support the case for a pure flying boat. Dr. Silvano Jung, as the maritime archaeologist who led the primary survey of the site faced a difficult task in verifying this geometry. The wreck is not a static museum piece, it is a deteriorating structure embedded in a dynamic tidal zone. Access is governed by the survey window. The survey window is the hard limit imposed by the rising tide, about 120 minutes on the east arm mudflats. The clock starts when the water falls far enough to expose the target, and it stops when the flood tide makes the site unsafe. In that narrow span, the team must cross the mud, find the diagnostic sections, clear silt, and record the structure, because once the tide turns, the site is erased again for another 12 hours. This constraint is compounded by the material condition of the wreckage. The aircraft is subject to a process known as intertidal preservation. This is a specific decay mode where the artifact is exposed to a wet-dry cycle twice a day. The constant oxygenation during low tide accelerates the breakdown of the aluminum alloy, while the anaerobic mud during high tide traps the corrosion products. The result is a transformation of the metal. The skin of the aircraft can retain its outline, but it loses the strength that once made it airworthy. Panels become friable and thin, and loads that would be trivial on a sound airframe can tear through corroded alloy. A surveyor cannot climb onto the wing or stand on the fuselage to get a better view. The weight of a human could break through weakened structure, destroying evidence and potentially injuring the researcher. Working from the periphery, the survey team examined the hull section where the landing gear would be located on an amphibian. There were no rectangular wheel wells, no door framing, just a continuous run of aluminum skin. This structural continuity provided the definitive method fingerprint. It confirmed that the wreck was a pure flying boat. When combined with the archival records of the 1945 towing operation in the aircraft's documented dimensions, the evidence chain was complete. The wreck in East Arm is the first Catalina of the Royal Australian Air Force. The most dangerous force acting on the wreck of a 24-1 is not the hydraulic pressure of the tide or the biological threat of the estuary. It is a chemical reaction that operates on a molecular level. The aircraft is not merely resting in the mud. It is actively functioning as a massive, unintended battery. To understand why the recovery of this airframe is structurally impossible, one must look at the materials used in its construction. The consolidated PBY-5 was built primarily of aluminum alloy, chosen for its light weight and strength. However, the flight control systems, the cables that move the rudder, elevators, and ailerons are made of stainless steel. In the dry air of a hangar, these two metals can coexist without issue, but in the saline mud of Darwin Harbor, they create a catastrophic electrochemical relationship. This phenomenon is known as galvanic corrosion. It is the primary constraint that dictates the lifespan of any submerged metal structure. The process begins when two dissimilar metals are physically connected and immersed in an electrolyte. The saltwater mud acts as the electrolyte, be a conductive medium that allows ions to flow between the components. The physics of this interaction are governed by the noble scale of metals. Stainless steel is more noble, meaning it is resistant to losing electrons. Aluminum is less noble, making it more reactive. When the circuit is closed by the salt water, the aluminum becomes the anode and the steel becomes the cathode. The laws of thermodynamics demand that the anode sacrifice itself to protect the cathode. The aluminum frame literally donates its electrons to the steel cables, dissolving its own atomic structure in the process. This mechanism explains the peculiar condition of the wreckage in East Arm. A surveyor looking at mixed metal runs may find that some stainless components appear better preserved than the surrounding aluminum, even in the same mud. But better preserved does not mean untouched. Chloride water can still pit and stain steel. The aluminum, meanwhile, sheds itself into white crusts and powders, losing section thickness until brackets and bulkheads no longer carry load. The strongest looking parts can still be the agents that accelerate the loss of structural integrity around them. This chemical trade-off creates a severe mechanical paradox. The parts of the aircraft that look the strongest are actually the agents of destruction for the parts that provide structural integrity. The skin of the hull, and which must bear the loads of any lifting operation, has been chemically hollowed out. It retains the visual form of a fuselage, but it lacks the tensile strength to support its own weight against gravity. If a recovery team were to wrap lifting slings around the hull and apply tension from a crane, the result would be immediate fragmentation. The aluminum soap would shear at the contact points. The fuselage would not rise as a unit. It would crumble into sections and destroying the archaeological context of the site. The mud, which currently acts as a corrosive electrolyte, also acts as a supportive cradle. It distributes the weight of the airframe evenly, preventing it from collapsing under the load of the tidal water column. Therefore, the decision to leave a 24-1 in situ is not a matter of budget or apathy. It is a matter of physics. The structural bond that held the aircraft together in 1945 has been replaced by a chemical bond that is dissolving the rivets and the stringers. To lift the wreck is to destroy it. The only viable path is to document the site as it dissolves, accepting that the stainless steel cables will eventually be the only components left, lying in the mud where the aluminum used to be. The aircraft is effectively a ghost, held in shape by the very sediment that is erasing it. When the structural integrity of a submerged airframe drops below the threshold for a safe lift, the recovery plan must pivot. The objective changes from saving the entire machine to harvesting its specific components. If the hull cannot be raised without disintegration, the engineering team must identify which parts are durable enough to survive extraction and significant enough to preserve the legacy of the aircraft. In the case of A24-1, that kind of selective removal happened much later, after the site had been inspected and documented. Following a 1998 check, a small team returned with a narrow objective: remove a specific exhaust component from the wreck to support the restoration of another Catalina being prepared for static display at the Royal Australian Air Force Base at Amberley. It was not a full recovery, and it was not a refloat. It was a calculated transfer of one durable, hard-to-fabricate piece from a dissolving airframe to a protected survivor. This is the logic of the partial lift. It accepts the loss of the primary structure to save the functional subsystems. The hull of A24-1 remains in the harbor, continuing its slow chemical conversion into the mud. But the components that powered it across the Pacific in 1941 are now preserved above the waterline. The aircraft was not saved, but its identity was grafted onto another survivor. This decision acknowledged that while the body of the aircraft was too far gone to be rescued, its parts could still serve a purpose in the historical record. In the final analysis, the wreckage of a 24-1 is defined by what remains visible. When the spring tide retreats from the east arm mudflats, the survey team is left with a fragmented skeleton of the first Catalina to serve the Royal Australian Air Force. The hull is split, the wings are shattered, and the interior is filled with sediment. Yet this debris field constitutes one of the most significant aviation archaeological sites in the Northern Territory. The current management plan for the aircraft is technically defined as in situ preservation. It is a heritage strategy that prioritizes site stability over extraction, keeping the evidence where it lies. After decades in the wet-dry rhythm of the flats, the wreck has reached an uneasy equilibrium with mud and tide, supported enough to remain legible, yet too fragile to be moved intact. To intervene now would not rescue the aircraft. It would disrupt that equilibrium. Removing the aircraft would require a massive expenditure of resources for a result that would likely be catastrophic. As established, the aluminum has degraded into a brittle, hollowed shell of alloy. Any attempt to lift the fuselage would cause it to crumble under its own weight, and turning a recognizable aircraft into a pile of unrecognizable scrap. By leaving the wreck in place, the heritage community ensures that the site remains available for future non-intrusive study as remote sensing technology improves. The site is also shadowed by a biological perimeter. The east arm is a known habitat for saltwater crocodiles, apex predators that can move through the mangroves unseen. Their presence is a powerful deterrent to casual wading and souvenir hunting. But it is not a wall. Crocodile risk in Darwin Harbor is actively managed, and the hazard is real precisely because it cannot be perfectly controlled. This leaves a 24-1 in a state of suspended animation. Delivered in 1941, it marked the beginning of the flying boat era in Australia's defense, and it made it through the Pacific War when hundreds of sister ships were lost to combat and accident. Now it serves as a physical marker of that conflict, accessible only to those willing to navigate the tides and the hazards of the harbor. The survey data collected by Dr. Silvano Jung and his team ensures that the geometry of the aircraft is preserved in the digital record, even as the physical aircraft slowly dissolves. The question that remains is not if the wreck will disappear, but when. Galvanic corrosion keeps eating the aluminum while tides scour the mudbank. Eventually, the structure will lose its cohesion completely, and A24-1 will become indistinguishable from the sediment of the East Arm. Until then, it remains a protected site, a monitor of the harbor's history, held in trust by the mud and the tide.